Hi, in this video we're going to be talking about the convergence and divergence of series. So let's start by remembering that a series, the sum of 1 to infinity of ai, is just the limit of a sequence of partial sums. Those partial sums here, Sn. So the sum from 1 to infinity of ai is actually equal to the limit of the sum of 1 to n of ai, which is equal to the limit as n goes to infinity of the sequence Sn of partial sums. So the sum of ai converges if and only if the sequence Sn, as n ranges from 1 to infinity, converges. And the same is true for divergence. So if the sequence of partial sums diverges, then so does the limit of our series. So let's take a look at an example. Let's take a look at a few, but let's start with the sum from 1 to infinity of n. Now, we can think of this as the limit as, say, k goes to infinity of the sum as n goes from 1 to k of n. Now, this is a special type of series, and the sum as 1 goes to infinity of n is going to be k times k plus 1 over 2. And we'll take the limit as k goes to infinity of this. And since we know that this diverges or goes to infinity, our sum from 1 to infinity of n is equal to infinity. So this series diverges. And let's take a look at our second example, the sum from 1 to infinity of negative 1 to the I. Now, if we just look at the sequence of partial sums, we see we have negative 1, 0, negative 1, 0, negative 1, 0, and so on. So the series does not converge to any number, so we can say that the series diverges. And we could see that either by just looking at it or looking at the limit of Sn for n going to infinity, and we'll look at S2n plus 1. Remember, we have the even and odd property for sequences. And if we look at the odd ones, it goes to negative 1. And if we look at the even limit, that's 0. So since these don't coincide, the limit doesn't exist. Next, let's look at 1 over n squared minus 1. So if we look at the nth partial sum, that is the finite series, n goes from 2 to infinity of 1 over I squared minus 1. And by breaking this up, we see that this is 3/4 minus 1 over 2n minus 1 over 2n plus 1. And now if we were to take the limit of our sequence, Sn, we get the limit as n goes to infinity. Let's put n goes to infinity for Sn as well, of 3/4 minus 1 over 2n minus 1 over 2n plus 1. And that is going to be 3/4. So the limit of partial sums converges, which tells us that our series converges to the same number. And finally, let's take a look at the series 1 over 2 to the n minus 1. So if we look at our partial sums, that's going to be the sum as n goes from 1, or k, goes from 1 to n of 1 over 3 to the k minus 1, 2 to the k minus 1, which is going to be 1 minus 1 over 2 to the n, which is just going to be 1. So our series converges because the sequence of partial sums converges, and we can just say that this guy here is equal to 1. Now let's look at an important convergence rule, and it actually doesn't really tell us anything about convergence, but instead talks about divergence. So the rule that we have here is that if a series converges, then the limit of the sequence that we're taking the sum of goes to 0. So we can get we can take the contrapositive of this, and we get this very important divergence test, which says that if the limit of the sequence is not equal to 0, then the sum diverges. And it's not true the other way around. So if we were to look at the sum of 1 over n, this is actually a divergent sequence, or a divergent series. But as we know, the limit of 1 over n as n approaches infinity is equal to 0. So this is our non-example. Now let's take a look at one that we actually can use the divergence test for. So we want to know the limit, or the convergence or divergence of this infinite series. So we just take the limit as n goes to infinity of the inside here. So 3n cubed minus 4n squared over 16n cubed plus 4n squared. And we know that the limit of this is 3/16. And since that's not equal to 0, that tells us that the sum of this guy must diverge. And the reason for this is because at the tail end of our sequence of partial sums, we're essentially taking everything and we're just keep adding 3/16 to it. So that's kind of the principle behind this, is if we look at our sequence of partial sums, or just the limit of the sequence or the series as we go towards infinity, we're going to have a1 plus a2 and all the way up to some a big N, and then we're essentially, not quite, but we're essentially adding 3/16 plus 3/16 plus 3/16 all the way on forever. Okay, now let's take a look at absolute and conditional convergence. So we saw that the sum of 1 over n diverges, but in fact, if we were to replace that 1 with a negative 1 to the n, it converges. So we call the sum of negative 1 to the n over n conditionally convergent. Okay, and so let's have a definition of what it means for something to be conditionally convergent and its counterpart absolutely convergent. So a convergent series is absolutely convergent if the absolute value converges, so the sum of the absolute values converge. And we call it conditionally convergent if the sum of the absolute value diverges. Now remember that our initial series has to be convergent. So if our initial series diverges, then there's no way it can be absolutely or conditionally convergent, because then it wouldn't be convergent, right? So let's take a look at an example. We've already seen this one, but let's just put it right there on the screen. So the sum of -1 to the n over n squared is conditionally convergent, but the sum here of -1 to the n over n squared converges absolutely. And let's go ahead and see why. So if we look at the sum of the absolute value of -1 to the n over n squared, as n ranges from 1 to infinity, that's the sum as n ranges from 1 to infinity of 1 over n squared. And as we'll see in a few sections, we can actually relate this sum to its integral, and that's called the integral test, and we'll see that in a little bit. But it turns out that this sum also converges. And that tells us that our original sum of -1 to the n over n squared is absolutely convergent. All right, and that's the end of our video for today. So we've talked about convergence, we've talked about divergence, absolutely convergence, and conditional convergence. We've done a couple of examples, and if you have any questions, comments, or concerns, please place them in the comments below. And as always, thank you for watching.